Great. Well, I'm glad to have an opportunity to show some of the things we've been working on over here, the Aramco. As Molly said, I'm here at Aramco Services Company. I'm in the Aramco Research Center, where we basically do front-end research for, front-end for technology, software development. We work with asset teams to help develop workflows and processes to solve some of the reservoir problems better. So in that role, also get opportunity to present at conferences and write papers, develop software. So there's a lot of variety, and so that kind of goes into this specific talk, which is some streamlined workflows for dealing with faults. If you've followed any of my stuff over the last several years, one of the things I like to do is kind of have a two-pronged approach to dealing with geomechanics of geologic structures. On one hand, there's really a heavy physics emphasis where we're trying to solve constitutive equations. We're looking at anisotropic damage mechanics, permeability structures, a lot of really the more detailed work where the goal is to understand in very high fidelity what's happening with the physical processes. There's another branch of the work though, which I think is probably the most relevant for asset teams specifically, and that's this idea of streamlined workflows. That's where we take some of those concepts, we try to boil it down to what are the most important things we need to solve reservoir problems. That might be a reservoir problem in a development or an exploration play, but even for just general structural physical processes, what are the key elements that we need to understand to get to the bottom of the questions we're asking? It might be a fluid flow question, might be a question about where we can put the well. And so today I'm going to talk about that second branch, which is really the practical side of geomechanical modeling and trying to hone in on some techniques that help us get to answers quickly, and then help us get to an answer that really people in various teams and different types of assets can explore with the tools they have available. So this topic is about faults, but not just faults, talking about fractures, geomechanics, stress, strain, kind of the world and the ecosystem surrounding faults. On the left is a picture of what we might think of as a typical fault. This one is near Molly's Castle, Utah. It's fault plane. There's a height, there's a finite height, there's a finite width, which would be the fault core. And if you get up on the fault, you'll see slicken sides, which give you a sense of the offset. You can trek around these things and you can see their limits and what their three-dimensional expression is. This is typically what we think of in fault space. It's just that through-going plane perspective. As we get into kind of a more geologic stratified setting, though, we recognize that that's not necessarily the way faults always express. So on the right is a block cartoon, a couple of block cartoons, where we see that, yeah, faults expressed as singular planes, but that tends to be in a more competent, really a more massive competent unit. So if we look on the right, let me get turn my pointer on. So if we look on the right, yeah, we might have a more competent unit where we have a through-going fault. But as we get to the extents of that, we might actually see the fault expressing as a pre-faulted folding, damage wings, damage zones, process zones, splays, all kinds of things that might happen outside of that main fault break. And so this is also where understanding the structure of the fault comes in play. It's not simply a surface that you go map, the kind of thing you might pick in seismic, but there might actually be some features that are surrounding those fault tips, and the fault itself may express differently. On the bottom is an example. You think of this as early or advanced, or you could even think of this as stratified, where a fault in one unit or in one time period might be continuous and through-going, but in another unit or in another time period, it might actually be segmented. And so in three-dimensional space, the fault might actually be segmented and continuous. And so this kind of lays out part of this discussion of getting the geometry of the fault correct to understand what its geomechanical implications are. Here's some cross-sectional views where we have through-going fault planes, clear breaks, but the clear breaks are separated by different types of expression in the different units. So we might have a largely undeformed region, but then very close to that same fault, we might actually see some damage zones and heavily fractured intervals. And so this kind of lays out this idea that when we're looking at individual faults, we need to remember that they're part of a fault system. And so when we're going to model these, we're keeping in mind what can we see, what can we not see, and how many of the faults do we want to include. So again, in the 3D block models, we see that these are systems of faults with different expressions depending on their timing, their orientation. And even as we look either in time, early advanced, in block model on the bottom, or this could be even a stratified, where we might see different expressions of the fault continuity. Faults may actually be very connected, or they might be segmented. And so this again kind of lays into this idea of fault systems as opposed to just single surfaces. Three-dimensionally is where it starts to get real interesting. This is what we're mostly interested in a reservoir context, or in a understanding the system and the evolution of the system. On the top is an example from a Saudi Arabian asset, published example, where we have a through-going fault zone, and then we have an anticlinal structure. We have different tectonic expressions. So the structure itself is a very steep fault that was not formed under contraction. This is probably a strike slip fault. But in the modern day, in the present day situation, we see expressions of the fold that let us know that there's actually some contraction as well as some strike slip tendencies. So we have complex motions on these faults that express themselves in the folding. If we look at a depth slice or a time slice through a reservoir, and this is just a textbook example, we might even see that the connectivity of the fault varies, where in some stages or in some horizons even, we might see no connection. And then as we go through, the faults actually link up and we see different folding expressions. All of this comes into this stratified three-dimensional or even a four-dimensional view of the reservoir of the units that we're dealing with, where we are interested in capturing what is the structural geometry, what is the framework, the skeleton for all of these fault systems. And so this is an example from Kuwait, where we have a fault expressing as a thrust. And then as we go slightly up section, we actually see some examples of normal faulting. So we need to make sure that what we're considering for the mechanics and the kinematics on this lower fault are not necessarily the same as what we would see up section. And so this kind of directs us to the idea of building a structural framework model that includes both the mechanics and the kinematics. So what is this structural framework model? Well, most simply, it's the skeleton, it's the horizons and it's the faults. The horizons that are captured with their offsets, the faults that are captured with their three-dimensional geometry. This is going to be the basis for almost all structural modeling that we do to try to get a geomechanics answer. Here's an example, and I'll show this case study several times through this talk, really maybe through the first 2/3 of the talk. It's an example from Utah. This is the Lisbon Valley Fault Array. It's sort of an idealized interpretation of a real fault system that is a long trend with you go a little bit further north and you're at Moab. So this whole kind of Moab fault system and the paradox. But this is just an example horizon. It's idealized where we see discrete faults and then we see offset horizons. So the combination of the faults and the horizons gives us a structural framework model. For what I'm going to show you, I'm going to show the discrete models that we have fault surfaces, slip on the faults. Depending on the solution type, there may be contact included, and we're looking at offset horizons. There is another type of mechanical solution that we can consider, which are continuum models. In this case, we would have gridded fault zones, equivalent fault properties that would allow us to shear both the fault zone and the horizon. So this is a different technique. I'm not going to talk about this, but this is out there also. So most of what we'll be dealing with are some different ways to model discrete faults that come from a structural framework model. For this type of model, the most important factor that comes into play is the slip or the offset on the fault planes themselves. These are not always going to be normal faulting, as some of the diagrams in my examples are going to be, but they could be oblique, they could change over time, they could be normal faulting in one time period and then oblique thrusting and reactivated in another time period. But in any case, these fault surfaces have a slip distribution and they have a direction. And these are the things we need to capture both as inputs and as results. So the modeled slip distribution typically forms an elliptical pattern that matches the throw distribution on the horizons. When we just map that directly, so this is, again, this is that Lisbon Valley example. When we map that directly from some of our outcrop measurements from some of the cross sections that have been published, we get a distribution that looks like this. If we superimpose or we impose an elliptical distribution so that we can try and capture some of the fault motion mechanics better, we get patterns like this. And so these are going to be the inputs for whatever method we use. These are going to be the inputs on those fault motions. So now we're at this structural framework, and we get to decide what kind of mechanical solution do we want to use. A lot of this is going to depend really on some logistical questions. In an academic setting, you can kind of take whatever approach seems novel and is your study area. In a company, you may not have every tool at your disposal, and you may actually need to decide what solution you're going to take based on the time frame that you have. And so if you're trying to get a lease bid out the door in a couple of weeks, you may choose a different approach than if you have 6 months where you're trying to build up kind of a holistic development scenario. And so which solution approach you use really depends a lot on logistical questions about what you have available and what your skill set is and the time you have to solve it. So if we start on the left with this example structural framework model from Utah, we have discrete horizons, we have discrete faults. These faults have offsets on them. The first approach we'll look at is really mathematically the simplest, and it's the quickest, and that's the elastic dislocation approach. So in this case, we're not actually going to build out a volumetric model. We're going to solve all of our stresses using just the fault and horizon planes. We'll use these fault motions and the fault slip distributions to make some mechanical simulations. And this is all going to be an elastic solution, a linear elastic solution. It makes the simulations run quickly, but it also limits what you can do. But we'll talk about why we might do this elastic dislocation approach. The next option that I'll show is the 3D finite element approach. In this case, we take the structural framework and we actually mesh everything in between, and we mesh the extremities, so the boundaries of this, where in this case, I'm showing a 3D tetrahedral mesh that is explicitly mapped to all of these surfaces and horizons. So it's a lot of work in there. I'll talk a little bit about the pros and cons of these approaches. The 3D finite element approach gives you a lot more flexibility with the physics, but the model building does take a lot longer. And then the third approach I'll show is the boundary element, or this elastic dislocation method combined with finite element. So a hybrid approach that uses kind of the best of both worlds to get a streamlined model out the door, bypassing some of the difficulties and really focusing on the strengths of each technique. And when I get to this, I'll switch case studies to a conceptual case study. But so let's go back to the Utah example. We'll run a few examples through here. So this is Lisbon Valley in the Paradox Basin. It's normal faulting. It's cored by salt. And there's a range of different motions. I'm not going to talk about the structural environment too much. I'm just going to get into the modeling. But I want to show you that this is just a case study that we're building out. Really, we've got some good outcrops and some faults, and I think a lot of you have been to Moab, so you know kind of the general geology. This summer, I've got a summer intern from University of Arizona, Lauren Reher's here. I'll show a couple slides with her work. She's continuing this Paradox Basin case study. We're doing some new collaborations with University of Arizona, so hopefully we'll get to work on these over the next couple of years, but we've been in talks to kind of build out this model in more detail. And kind of the idea of building a very constrained 3D structural framework and being able to do these elastic dislocation simulations using real data, using real calibration and benchmarking work. So to do this elastic dislocation modeling, I've used a tool that I developed for Aramco. It's a proprietary software that's built in MATLAB. So this is one of the projects I was working on over the past few years, was to code this up and get it running. It's got three main modules. It's the elastic dislocation module, which is the 3D stress and strain fields. This allows us to get to the tectonic deformation as well. So like the kinematics of that, but also in situ stress perturbations. This could be around faulting, and that'll be the example we show here. But this model actually can be used for hydraulic fracturing as well. There's an ARMA paper I've got in 2019 where hydraulic fracture swarms were input instead of faults, and stress shadows were calculated. And so this, it's kind of a general approach that can be used for a lot of different geoscience applications. Here we'll focus on faulting. The tool also allows you to do kind of some basic Zobakian critical stress solutions. So fracture stability, dilation potential, and this under static stress conditions. And this is actually a real helpful tool for a lot of the problems that we're solving and trying to understand. So, stress stereo nets, what under applied stress field, which faults we expect to slip. That gives us some input also into how we set up our boundary conditions, how we set up our slip perturbations. And then of course the more diagrams and some of these things that I think probably many in the community are familiar with. And then the other thing we'll touch just briefly, the ability to do fracture predictions. So being able to take these solutions and then predict natural fracture sets. I won't talk about this whole package very much. I just got done at ERTEC presenting this. There's this conference paper, and then there's an online talk that you can look at too. But I talk about this software, just a kind of a high level summary of what it does, and so you can go check this out if you're more interested. It is proprietary, so it belongs to Aramco, but you're welcome to look and get some ideas for your own work. So here's the interface. It's a single interface, and coming back to that original theme of trying to streamline the work that we're doing, this is really what this software was designed to do, is to take all the possible structural geomechanics operations that we know of and really boil it down to a few that might be most important for a limited set of structural problems, a limited set of reservoir problems. So this allows us to have a geometry input. So we input tri-mesh surfaces. This comes from seismic interpretation if you have 3D seismic, but this could also come from DEMs, from interpreted cross sections. The Utah examples are coming from basically in Move, in Midland Valley Move, or in GoCAD or Petrel or somewhere else, building up these 3D geomodels based on field information and then inputting that into this proprietary software. The stress input is relatively simple. It's a linear elastic half space. So in this case, there's not a lot of parameters that go into it. Young's modulus, Poisson's ratio, and then for the critical stress stuff, we have coefficient of friction. The ability to put in a background stress, so that can be a log stress, or that could be a 3D stress tensor, and that's about it. So that's kind of this topic about when we're guiding the asset teams through the properties they need to use. Part of the approach that I was trying to hone in on is saying, well, what might you get from logs? What might you get from some basic core and plug data? We don't always have the real complicated constitutive equation type parameters, but usually we do have elastic parameters. So that's what these tools are based on. Then the modules, the dislocation, the prediction, and the stability modules are all pretty easy. You can see there's not a lot of buttons to push. You need to know what you're doing to get through the software, but again, really trying to simplify the tool down so that the user isn't wading through theory and isn't wading through a lot of complex workflows, but can pretty quickly navigate the system to get to an answer. And then this is a visualization. Again, pretty simple. You can export these. You can manipulate in MATLAB in a lot of different ways, but really the user has some simple visualizations. So that's what's summarized here, the last few slides in these bullet points. Specialized code, it's editable, it's tweakable, focuses on boundary element code and analytical geomechanics. So that simplifies the rock mechanics element, simplifies what we can do for tectonics. But again, the goal is to get to a streamlined answer, not necessarily to solve all of the complex physics. So here's an example of that applied to the field. So this is that Utah example. The structural modeling software is used to generate slip profiles, run the perturbation models, and predict natural fractures. So this is that slip offset data that's input on the faults. These are first run on a kinematic model to get some of the layers offset appropriately. And then a smaller distribution is run to get static perturbations or in situ stresses. So here are the deformed horizons. So you can get some ideas of incremental X, Y, and Z displacement. And again, the idea is to be able to do the kinematics and the mechanics. So this is, top is testing the kinematics, bottom is testing the mechanics, so the perturbation model. So won't go into the patterns very much here. You know, I think at the AAPG talk later this year, we'll have more detail on some of these images. So you have to wait a little while, have to wait a month to see some of these results. But mean stress and strain, total stress, total shear stress. So all of these are the kinds of things that a user might want to simulate to ask some questions about fault connectivity, about preferred flow conduits, about distance, safe distance to drill from a fault likelihood. Yeah, so we have a lot of things that we can predict from these attributes. The software also allows us to do predicted fractures, so predicted the joints. Here are the orientations, and then here are the orientations in map view predicted on the grid. So these are tensile fractures, and then these are shear fractures. These are actually polymodal fractures. So in some zones we see conjugate faulting, and in some zones we see a result of orthorhombic strain. So this is a talk for next month. We'll get into it later. But you know, the idea here is the user with very simple inputs can go through that interface and without too much trouble can run all of these simulations, can predict the fractures, and can start making some pretty reasonable decisions about the reservoir. Okay, so what if we said, I don't want the boundary element, I want to do more complex physics, or I want to look at different layer properties? Well, in that case, we would have to update and go to a finite element approach. So yeah, the finite element approach, it actually allows us to take these ideas that we were doing in the elastic dislocation solver, but now we're applying those volumetrically. So we've got this tetrahedral mesh, we've got a pretty complicated network where we have to get the elements right, we have to get the horizons right, we have to get the fault surfaces right, and all of this has to be airtight. The frictional contact has to be applied, and then we can also apply magnitude of the slip direction. One of the benefits of finite element method is it's easier to put a unique boundary conditions, so the tectonics can go in there quite a bit easier as well. So what do we get out of the elastic dislocation model? And we'll do kind of an A-B on this slide and the next slide. The elastic dislocation model, again, requires very little manipulation of input surfaces. And just point out this, some of these next two slides, there was a talk at ARMA a month ago, and so you can look at that ARMA paper to go into a bit more detail on this comparison. So we take this right from the structural framework, we can go right into the elastic dislocation model. All we need to do is adjust the mesh to the desired resolution, put the elliptical slip distributions on, and now we're able to do the ED results. And so this is really just honing in on kind of the A-B of the finite element and the ED model. Here's the ED model where we're looking at a depth slice. Mostly on these ones, we're looking for the patterns, not necessarily to calibrate or benchmark it, but I think put in the back of your mind that we would, in an ideal scenario, we would have field data. We would have some wells with stresses. We would have some core, some natural fracture data. We would have some outcrop data, and we would try to match these results to the real data. And so that's another step. It's not a step I'm going to talk about much here, other than to say it needs to be done. But when we do these results and the model results, we're going to look and say, yeah, am I getting the general answers I'm looking for? Am I getting the offsets correct? Is the right side of the fault going up or down? Is the fault shearing in the right direction? And are the magnitudes about right? So you can kind of see here what I've modeled is 0.07 meters. So just some small displacements due to this fault. Now we're looking at perturbations. So are we seeing, what magnitude of perturbation? These are pretty small, less than an MPa. The idea here is just to start looking at the patterns, not to bring the rock into failure, not to bring it into plasticity, but to just start looking at what are some of the geomechanical interactions. So here are very, very small stress perturbations, but we're looking to see, yeah, we actually get different results on the upthrown and downthrown blocks. When we're in between faults, we see more complex interactions. When we're at the tips of faults, We see some of these butterfly patterns. So yeah, we're seeing some of the stuff that we would hope to see. We see intensity changes. Here's principal stress. So this is kind of what we're looking for is do we see some realistic geologic patterns? And then when we have real data, then we can start working on the benchmarking and calibration. Here's that same model, but instead of being run with the surfaces on the elastic dislocation approach, this is the volumetric approach with finite element solution. Now, the first thing you'll notice if you were paying attention is I started out with a bunch of horizons. And on this model, I ran the model and I took the horizons out. So I talk about this in the ARMA paper. For this specific model, the reason I did that is because I was trying to kind of pace and get both models, both the construction and the simulation time to be about the same. So saying what would it take to get these models to from kind of start to finish about the same time period. And in order to do that, I had to take the horizons out because I was going to have to go back and do a lot of remeshing, a lot of mesh optimization, and it was basically killing the simulation. So you can go back and do this, and you're going to need to do that to get a good simulation. But in this case, we can still look at the elastic approach, and we can just take a depth slice through these discrete faults. So the 3D view shows you, yeah, we're getting the same kind of things, but now we have the benefit of being able to fully slice in and out of the model. We can take these cross sections, we can do R-blinds, we can do ISO surfaces, we can do all kinds of fun stuff in three-dimensional space. If we just look at the depth slices, so to kind of mimic what we saw on the previous slide, yeah, we're also getting, I would say, reasonable results and similar magnitudes. We can make sure the right sides of the up and the down thrown blocks are correct. We can make sure that we're seeing some of these lenses or these intersecting zones are behaving in the same way. In terms of stresses, we're looking for the same things. Are we constraining the magnitudes roughly? And now you'll notice that this magnitude is different than the previous one. And in this case, I was also trying to keep it below failure stresses, tensile failure stresses specifically, but they're not the same. Patterns are also not exactly the same, and I'll kind of go back and forth. And you'll notice that the patterns are similar, but not identical. And this is something that I address in the ARMA talk. But a lot of the reason for bringing this out is just, a lot of times you say, well, what happens if I build the same framework model and then I just run it with my favorite tool? Well, you can do that, and there might be a good reason for doing that. But just be very careful, and this is a case study to kind of demonstrate, be careful that you shouldn't expect, if you run this in the proprietary Aramco tool, and then you go run this in the finite element, commercial finite element code, and then you run this in a commercial boundary element code, I wouldn't expect, and don't go in expecting that you're going to get similar answers. That process of calibrating between models is another step, another thing that needs to be done, not just benchmarking the field data, but benchmarking the models to make sure that the way you're inputting the results, and also the underlying physics assumptions are different. So making sure that you're accommodating for that in order to get similar stress and strain patterns. So in this case, I wasn't able to accomplish identical results, but I think both present pretty usable results. So if you went either direction, I think you'd be okay. But now let's decide, why would I go one direction or the other? Okay, so here's a chart where I compared why finite element, why elastic dislocation. So multiple faults. FEM, it was actually pretty difficult to get all this meshed. In the ED approach, very easy. Intersecting faults. So for finite element, it's actually very difficult also, a lot of meshing issues. For the ED, it's very easy. Unique slip distributions can be input on either type of the model pretty simply. Contact properties, again, you see differences. What ED doesn't actually handle a lot of that, but the intersections and meshing is very easy in that approach. Finite element allows you to do layer properties, inelastic properties, etc. So you can kind of decide what you would want to do based on how complicated it is. If we look at the structural framework workflow, the left side is what I did with those two models. The elastic dislocation was pretty simple. Refined this, once I had the framework, I refined the surface meshes. I ran the simulation, looked at the results. If I didn't like them, I just reran it and changed some of the properties. Very simple process. Finite element is quite a bit more difficult, taking those surface meshes and refining them. and then having to export them and build out a 3D mesh. This requires, in this case, I used an automated meshing wizard in a commercial software, but you could also use a manual meshing tool where you kind of in a manual hand by hand kind of thing, going and picking elements and adjusting nodes and stuff like that. In either case, you're going to have to do element quality checks, simulation stability checks, and then you have to go back and rerun these things to get a stable answer, and also to get a good answer, a meaningful and accurate answer. So finite element is a lot more complicated, but you do get better physics and more advanced physics. So with that, I want to jump to another case study where I do a hybrid simulation. So I say, well, what if I want to combine the two approaches? I want to use what's easy in this approach, what's easy in this approach, and the goal is to sort of streamline my way through the easies. I want this part to be easy, and then I want this part to be easy, and I'm going to ignore all the stuff or try and avoid the stuff that's hard. Okay, so that's this case study, and this has been published in Interpretation earlier this year. So if you go to the SEG website, you can download this, or it's on OnePetro. And this is a case study where I go through this process of merging the two types of model, creating a workflow that combines them. And the ultimate goal is to answer something about stimulated rock volume. So we're going to move through that space, and then we're going to do hydraulic fracture simulations. And then the goal is to assess, does structural position matter? And I think you're here and you're in the group because you agree, or your experience has shown you that structural position does matter. But in this case, we'll go through the simulations to build out a case study to sort of document how it matters and what you need to include to capture that it matters. So this is the basic idea between merging the two different types of model. So this has been lumped into what I'm calling, or what I'm at least framing as, multiscale modeling. And this is the idea of, we're going to use for different scales of problem, we're going to use a different technique. And then eventually, as we get towards hydraulic fracturing, we're going to go zoom in closer and closer until we get to the point where we actually are modeling the high resolution geology and the hydraulic fracture propagation. But we're going to capture up front the structural framework model. We're going to run a background stress model with the finite element approach. We're going to run a perturbation model with the elastic dislocation approach. We're going to use elastic superposition methods to get into a hybrid model. And then from this hybrid model, we're going to use a submodel boundary condition approach to core out a zone of interest, which we then run again with high resolution stratigraphy. So there's a whole paper behind there. We're going to just kind of zoom through that. But the main thing is to kind of show you how you merge some of these processes to focus on the streamline aspect. So this is a case study that we're not in Utah anymore. Now we are in Kuwait. We're looking at a structural framework that loosely comes from some sketches from Richard et al. He's got a series of papers where they're looking at Sabria Ridge and some structures in Kuwait. I've taken this model and using some kinematic approaches, I've created some faults. I've disturbed them, and I've created some offset horizons. So we've got a generic conceptual framework model that more or less looks like this Kuwait case study. I'm going to take the geometry and I'm going to ignore everything else about the problem. So I'm just ignoring all the specifics and focusing just on this geometric pattern. So then what I've done here is I've built this up as a 3D structural framework. I've dropped 3 wells with mechanical stratigraphies. These will be hydraulic fracture simulations eventually. These are just arbitrary. I placed one over here, one here, and one here. It doesn't really matter why they're there because it's a make-believe problem. But conceptually, the question is, if we're close to the fold, or if we're close to the fault, or if we're kind of out off structure, would we see different responses solely due to the structural proximity? Okay, so to get there, we go through that workflow that we showed just a slide or two ago. We build a 3D background stress model. This time we're actually using the finite element method so that we can capture this broad three-dimensional pattern with both the XY pattern and also with depth. We've got the faults in there, but the faults aren't really doing anything. So we're ignoring fault perturbations here. And the reason we're going to ignore the fault perturbations is because really what we want from the background stress model is just the stress patterns. We're going to get the perturbations from this 3D stress perturbation model. So these are this ED simulation approach. Here's some cross sections just to give you an idea that yeah, there are some real some real patterns here. There's these are scaled for certain reasons to not get into failure stress and all that. You can read the paper to kind of go through this in more detail. But then these are combined using geomodeling approaches into a 3D total stress grid. So now we've got this volumetric model that contains perturbation results from an ED model, finite element background stresses, and then the whole thing is this tectonic or this broad scale, asset scale structural model. From that, we're now going to zoom in and we're going to core out some stratigraphy. So this is SRV1, SRV2, and SRV3 that are located on the structure. These are given identical stratigraphies, so mechanical stratigraphy is the same. This comes from an Arabian plate case study. The depths and the properties don't really matter, and they definitely don't belong in the structure I put them in, but it's just a conceptual model, so it doesn't matter. And then from this, we run finite element simulations. And so this is kind of just a standard. In this case, it's run using a DFN code, but we're getting these hydraulic fracture patterns that come out of this near wellbore behavior. So what has happened now because of using structural perturbations from the far field as well as from the faults and faults? Well, if we would only run, sort of a standard commercial frac simulator, stresses would be identical. Depths would be different, but the stresses would be very, very similar. What we were able to do by using this approach, though, is we're actually, even though the stratigraphy is exactly the same and the perforation zone here shown in pink are in the same intervals, the stresses are different. Here's an example showing the closure stress or the frac gradient or minimum principal stress, or SH min in this case as well. Just notice the difference in intensities, the difference in the distributions between the three stimulated volumes. Now, the only reason that these are different is because of structural position, because the mechanical properties are the same. So by including the tectonic and the fault stresses, we're actually getting different results. And this is what that looks like if you core it out and you just look along the wellbore at stress profiles. So you would not get these results if you just used Eaton's equation, a 1D stress log equation. You wouldn't be able to capture these differences. And then you run through those differences and we run hydraulic fracture simulations. So there's in that 2019 ARMA paper, we go into some information about how, what properties I use to simulate this. Not gonna talk about it in detail, but I do want to just identify that if you look at the different structural locations, the injection properties are the same, the mechanical stratigraphy is the same, but the ranges of hydraulic fracture patterns are different. You get different responses. This is surface area. So this is run a bunch of times, different stochastic realizations, different surface areas, different fracture patterns. SRV2, actually, you even get some intervals that have horizontal fractures. You don't see this in SRV3, where you get a lot of height growth. So you can kind of walk through this. You read some of the papers to figure out what the details are, maybe if you're asking some specific questions. But the idea is that by using the information from these different models, we're able to pretty quickly get to the ability to run structurally dependent hydraulic fracture simulations that are built on a structural framework model. So it's a real structural framework model. It's got the tectonics, it's got the faults, but we're also able to pretty quickly get in and streamline those approaches in order to get to what the business question is, which would be hydraulic fracturing. The last thing, and we've got running up on time, is I want to show you what we were working on this summer. So this is an extension of the elastic dislocation modeling. Just a few slides from what Lauren Reher, she's a fourth-year PhD student at University of Arizona. What she's been working on for her research is Salt Valley, a case study in the Paradox Basin. So here's kind of a map view of structures that she's been looking at. She's gone out and collected a lot of field data. So natural fractures, specifically she's looking at conjugate fault patterns related to both the fault and the salt wall collapse structures. And so this is kind of a great case study. It's a long trend with Lisbon Valley. It's a long trend with Moab. And so this is an area that we're interested in understanding, because there's really some good field data, and there's a great structural story here. But one of the things she's been looking at is trying to understand, as you get further away from this fault and further away from the salt, and there's some combination of the geomechanical interaction here, as you get away from these structures, she's noticing that you do get a difference both in the fracture orientation and in the mode of conjugate shearing. So she's seeing different bisector angles in the conjugate shears. And so this is one of the things that she's been working with us, is building up a case study, so a structural framework, and then running some simulations to try and predict and model with the field data as a benchmark. So she's gone in and she's built out 3D structural frameworks. She got some cross sections that she's worked on and worked on both the restorations, and then also just trying to build out an airtight framework. So this has been a chunk of work that she's done in reconciling the structure. And this is an example of what one of these structures looks like in the study area. So you kind of see there's this salt wall feature, and then there's a series of normal faults on the crest of the structure. So there's some timing issues, there's some kinematic issues. I'm not going to take the time to explain that, and this is really Lauren's expertise to kind of walk through this. But the whole idea is right at the beginning of the presentation, what I introduced is the need to build a realistic structural framework, and then to be able to test out some modeling scenarios. And so in this case, she's used the proprietary Geomechanical software, and she's been simulating strain and fracture patterns. I wish I would have had some of her results when I sent this in for approval, because she has some really cool images. She has some really cool perturbation results. Hopefully that'll come out in a public release, maybe later this year or early next year. But she's continuing to work on this, and there's some very cool stress perturbation results as a function of both salt withdrawal, where the salt is used as a dislocation surface, and then also modeling these faults as dislocations in their tectonic state. So very, very cool stuff. Hopefully we'll show some of this in upcoming months. So to summarize, and leave room for some questions, and then you can get off of your lunch break. There are more than one way to model the effects of faulting. So I would just leave you with my experience, but then also with the idea of, when we're trying to streamline these processes, don't get locked into one method. Some methods may be better for certain things. Others may be, they take a long time, or they may be real fast. And so don't worry about having a single method that you've mastered. I would say really try and focus on having a few methods that you could go to, and you can pick to tailor to the types of problem you're solving. No matter what approach you're going to use, I would recommend you build a quality structural framework. And this is a large investment. It really requires having, if it's field data, you need data collection, geologists. You've got to have a lot of skill set in that. If it's seismic data, that's working with both your geophysics and your structural geologist, a good framework model built up. But once you've done this, now you have at least 3 methods. You have an ED method, elastic dislocation method. There are some commercial tools for this. We have a proprietary tool for this, finite element methods, and also I've shown you the backbones for a hybrid approach that you could try on your own examples, where you would combine ED and FEM to get to a model using some geomodeling superposition options. So there's a lot of things we could do here. Ultimately, I think for the petroleum side, we're looking to get to some specific questions. In this case, I showed you an example with hydraulic fracture and stimulated rock volume characterization. But I think you could just as well, you talk about fault seal, you could talk about containment. This could be used for development plays, different stresses. Like the salt problem, stresses around a certain structure, stresses at different time periods. So there's a lot of things that we can do when we've got a good structural framework model and we're willing to take that geomechanical modeling direction. I think with that, I'll stop. And I appreciate your time. And I'm thanks so much for letting me take this lunch break with you.
Awesome. Thank you so much, Seth. That was really cool to see all those different methods and how you looked at those perturbed stress fields. It's something I love to kind of play with in software and then learn even more about. So that was very informative. Thank you. We did have a couple of questions come through and I can read those to you. Let's see. The first one is from Richard Schultz. He's asking, I'm wondering about how often you find including diagenetic sealing of fracture and faults calibrated from core or other data in critical slip and other outputs, and in general, is this considered a useful tweak by an asset team in areas where this process might be important or suspected to be so? He also says, nice work, Seth, and thanks for presenting today.
Yeah, and Rich already knows the answer to this. It's a trick question. Yeah, it depends. It depends on the it depends on the problem you're solving. If it's a fault seal problem, a lot of times if it's fault seal, we might be looking at a high porosity reservoir. Some of those Utah examples would qualify as that, where we have high porosity structures. The fault zones would be sealing. In that case, what we would be looking at is there a gradient as we go into the fault zone? In that case, maybe reservoir properties and fault offsets from a stratigraphic perspective would be much more important than the perturbations. Perturbations might be important if we're looking at understanding the connectivity. So is there a sealing fault, maybe not on the fault plane itself being a problem, but is there a problem around intersections where two faults or a set of faults are connected or are linked up, and that creates a vertical conduit. And so in that case, the perturbation might actually be very important. And so, so I think it really matters if you're dealing with seismicity, of course, then that's important, and the slip is going to be important. If you're dealing with sealing properties, then maybe the present day slip isn't that big of a deal, but the properties of the fault zone and the width of the fault zone is more important. And so you might choose a different technique, or you might, the way you model that technique might be a little bit different.
Yeah. Awesome, thank you. I guess I have my own question if I can ask. So whenever I'm in Google Earth, if I go to that fault around Moab, and I think if I'm on the southwest side, I can actually see some fracture patterns on the surface, and they tend to rotate around that fault. Is that something you or Lauren has looked at or tried to model?
Yeah, so that's actually a lot of the, so University of Arizona is continuing, they're doing great research in the paradox. Lauren specifically is addressing this around Salt Valley. And one of the big questions there, and I think the elastic dislocation model method is very helpful in this case. One of the big questions is trying to detect, are these faults, are these fracture patterns, the way they're rotating, the way they're intensifying, are they related to the faulting, or are they related to the salt? It might be diapurism, it might be collapse. There's probably a combination, and reconciling that with different phases of deformation is very important. So that's actually one area where I'd say an ED method is actually more useful. You don't have to worry so much about doing a lot of iterations on the framework model, but what you might be able to do is do a lot of iterations on the driving forces. You might want to do that pretty quickly and to compare a lot of scenarios. What if I use all salt withdrawal and no faulting? What if I use 50% faulting and 50% diapurism? So you have a lot of things that compare to see if you're getting your motions correct.
Awesome. Yeah, I look forward to seeing some more of our work, and I'm going to go dig out your paper from interpretation. Looks good. All right, we had a couple more questions come through. One from Mahdi Haddad. In slides 13 and 14, what is the process that leads to such small shear and normal stress changes? Is this only the geostatic state that the model reaches due to the presence of the fault?
Yeah, so regardless of the method you use, there's sort of an ongoing question, and if we're talking about static stress state, part of the question is what amount of the perturbation is actually attributed to a large fault offset. So we can think of aseismic slip or seismic slip. Just to be fun, let's imagine everything makes a big earthquake. In order to get a certain stress state, you know, think about would this amount of slip, would a meter of offset, which gets me the right patterns, is it realistic? Did I ever see a magnitude 9 earthquake, right? You know, so you kind of say, or you can kind of work the other way and say, if I put this much slip in, it gives me an earthquake. Maybe that was an earthquake that actually happened, or a series of earthquakes, but it brings me to gigapascal stress perturbations. Then you know that's not realistic. Also, that the elastic stress release probably wasn't the only mechanism, that you had failure, inelastic failure, plasticity, fracturing, aseismic slip. You know, you have a lot of things going on also. So yeah, I think you're right, Mahdi. There's a give and take, and for the ones I showed, I really didn't take a lot of time trying to reconcile with benchmarking to field data, but I think that's what ultimately you need to do is to try to figure out how much stress change maxima would you expect, or for the structural deformation, what is it that you're actually trying to model? Is it a slip period, or is it a time period, or is it a fracture event?
Yeah, good question. When I started studying these models and I saw the outputs, I kind of had those same questions about why is everything so small? But good answer. Yeah. Okay, next question is from Brett Fossum. Says, Seth, on your list of considerations on slide 15, those are quite useful. However, I expected to see also maybe faulting regime, normal versus reverse or strike slip. Given the fault regime is not on your list, are you suggesting that these methods you are showing are okay for all faulting regimes?
Yeah, and that's actually, you know, for me, when I'm talking about a streamlined workflow, that's part of what I'm thinking about also is, for every reservoir, for every asset, and even if I'm just thinking about what are, for Saudi Aramco, there are different structural regimes, and I don't necessarily want to have a different software for every asset type. There may be some reasons that we have to do this if we want a detailed study for some reason, but part of what I would consider in terms of just being practical is having some approaches that if you want to model, maybe in the present day it's a strike slip regime, but in paleo stresses it formed under reactivation and inversion. And so I don't want to necessarily have to change techniques every single time I'm looking at either a different field or a different asset, or even different structural evolution. So yeah, I think you're right, Brett, is identifying, does the approach I'm selecting allow me to do a reverse fault? Does the approach allow me to do normal faulting that turns into strike slip faulting? The ones I showed, yes, you can do that. But you're right, not every technique is going to be very good for that kind of that broad approach.
Awesome, thank you. Another quick question from Satya. He says, thanks for the great presentation. Is the hydraulic frac simulation in this case using pore elastic considerations?
Simple pore elasticity. So this is done doing a DFN software, commercial software. And so yeah, there's not a dynamic pore pressure response, but there's an effective stress correction. But yeah, that's something, and that's a challenge you have to think about when moving from the tectonic framework into the kind of the operational wellbore scale, which is a time scale difference as well. You know, a millions of year slip response that gives you a perturbation, or versus a minute's perturbation, which might come from your hydraulic fracture, stress shadow, or tip stresses.
Awesome. And another quick question from Edgar. He says, nice work, and nice work on the faults and fracture analysis techniques you've developed. And then ask, could you share what you typically use for the fault friction angle?
When in doubt, go with 30. That's layer dependent. That depends on the rock type. So if you're able to get the data, or if you ever pull off the data from the lab, or pull it out of literature, you know, a mudstone's going to have a different response than a brittle carbonate, or you know, or so, you know, whatever it is. If it's poorly consolidated, it might be more like 45, right? So if you're, some of those faults in Utah probably formed under a weakly consolidated or even an unconsolidated state. In that case, you know, maybe it's a higher friction angle. But yeah, you got to figure this out with your rock type and the time frame.
Awesome. I love rule of thumbs, and that 30 degrees is usually what I go with as well. Some comments, questions from Bob Davis. He said he didn't know that I had a castle in Utah. I did know that. I've never been there, but I'm going to claim it. And it's not a B&B, but you can set up a tent and enjoy it that way.
You can go camp out at Goblin Valley. So it's right by Goblin Valley State Park. So you can go hike around and look at the little goblin-shaped knoll thingies, the little wind alien patterns, and yeah. So you can go hike around and then go camp out.
Oh, I need to go. And then question about commercial software. I think you mentioned that the one that you developed is proprietary, so that's not available commercially, right?
Yeah, that one's proprietary. The elastic dislocation is proprietary. The Finite Element code and the DFN code that I showed are commercial.
Okay. Okay. I think you answered this for me, but what softwares were those?
The Finite Element was Abacus, and no, actually, I think I did. I think for both of those, I use Abacus a lot. For those, I used FracMan actually for both. So I used FracMan for the Finite Element, and I used FracMan for the DFN.
Okay.
Hydrofrac simulation. Yeah, both of those I think were FracMan.
Cool. Here's a fun question. It says, thanks for the explanations. I'm wondering, would you like to define the correlation between strike slip and pull apart basin that you could be forming the flower structure in that basin?
Yeah, so so that, you know, what a pull apart basin, you know, so you have pull aparts and push ups, and these are just when you have steps in your strike slip direction. If so, your strike slip direction is going like this, and if you have kinks or steps, then it either goes like this or it goes like this, depending on the motion. So if you're looking at map view, you know, you could either pull apart or push up. So yeah, so that'll depend on if there's a geometry change from the relative motion of the strike slip system, and then yeah, whether or not you see deviation in the dip of the strike slip faults, and a lot of times you do. Sometimes, you know, flower structure, there's debate kind of on whether that's a kinematic or a mechanical definition, and in any case, I'd say, you know, map it out with the stratigraphy. If you start to see splaying strike slip features as you go up section, see if you can figure out whether that's related to holding, whether that's related to mechanical change, whether that's related to different stress state up section. But again, you know, part of the interaction between structures and the little, you know, the way the faults are not always perfectly parallel, those will create some of these structures even with depth.
Awesome. Thank you. I'm going to grab a couple questions from the chat real quick and just take a couple more minutes if you have the time.
Yep.
I have a question from Colin, maybe two questions. He asked, you seem to be using stress boundary conditions any comments on why you prefer these over displacement boundary conditions?
So it depends on the software you use. The elastic dislocation model has no boundary conditions. It only has a dislocation along the fault surface. So it uses a slip vector, and then it perturbs the system. And that the way that this elastic dislocation technique works is the strain and the displacement are the perturbation, and then you do a superposition with a background stress. So the ED model does not actually even use a far field boundary condition in this case. The finite element solution can use either strain or stress. In that case, if you have a stress gradient that you can rely on, so if you have some wells and you know that you have a gradient that's reliable for the area of interest, then I think you can use that stress as a boundary condition. If you're looking at tectonics, so you know that you have overall contraction in this area or a rotation, some sort of a wrench zone or something, then you would want to use strain. Typically I like using displacement boundary conditions. The sub-modeling, so when I went from the big model so that hybrid approach, when I went from the big model down to the local layer scale model, that sub-model, the boundary conditions are the displacements that are pulled out of the big model. So it's kind of a combined approach. But yeah, it depends on the technique, and it also depends on what data you have.
Okay, awesome. And then I'm curious about this one too. How are you dealing with the fault damage zone in your simulations? Have you used the results of AVO inversion to populate the damage zone properties? And do you have any comments on that?
So you cannot do that with elastic dislocation because it is linear elastic and uniform. So if you use an ED model, this software or any commercial software, you're kind of limited to elasticity. And so you have to have some other considerations or some other assumptions if you're going to use that approach. With finite element, you can put in whatever you want. That just depends on how complicated you want to make your meshes and your geometry. So yeah, if you want to take seismic attributes that you get from any, you want to use anisotropy, you want to use coherence, you want to use AVO, you want to use things to create some zones around faults. You can totally do that with finite element approach. It just makes your model building more complicated. But yeah, you can do that.
Awesome. And have you ever modeled salt diapirs using the elastic approach?
That's what we're doing this summer.
Awesome.
What you will run into, and I'll give you a caveat. If you're going to do that, you can use elastic dislocation. If you do large strains, so if you're actually doing diapurism and large collapse structures or something, you can't use the stress results that come out of that because they're going to be really high. But you could use that to get a kind of an approximation of kinematic model. Now if you do it that way, the constitutive law is wrong. You want some creep or viscoplastic thing, but yeah, you can approximate the motion that way.
Awesome. And then last question, this was kind of a follow-up from Madi's question. It says these small shear and normal stress changes may be due to zero normal displacement boundary conditions, in contrast to more realistic stress boundary conditions that may lead to larger stress changes due to fault presence and harder to solve numerically. And then he's asking, Can you elaborate on the stress/displacement boundary conditions that these models can consider? I don't know if you maybe kind of answered that already. But.
Yeah, I think I kind of answered that already, but just to kind of state it a different way, elastic dislocation doesn't do great with tectonic boundary conditions. There are some commercial codes that have been developed that have kind of have some workarounds for that. But you're mostly looking at superposition for the elastic dislocation model, ways that you do that. If you really want to get that right, you probably need to go to finite element or something with a little bit more robust physics.
Awesome. Thank you. Those were some really good questions. I feel like they were challenging and you did awesome. So thank you very much. And
did I pass my PhD exam?
You passed with flying colors. So great job. Awesome. Well, thank you very much for taking the time to speak at our webinar today and talk on such a fun subject. I believe everybody enjoyed it. There's comments in the chat saying great job and great summary. Thank you. So much appreciated.
Thank you for the invite.
Yeah, thank you very much. We should have this video available on YouTube soon if you want to go back and also take a look at some of those references and publications that Seth put out there for you guys.